Welcome to another episode of Dominic Does DIY. So this is going to be episode number 2 regarding the op amp. In the first episode, we were understanding how we can spec an op amp out with some of the few specifications that we need to be aware of. And in this episode, we are going to look at one of the applications, which is the comparator. So the comparator takes the in minus and the in plus pins, but you can see it does not have any feedback going back to the output. And so the output will be a high gain output, which will basically rail the output to either VCC or VSS, depending on the inputs from the in minus pin and the in plus pin. So the basic formula for the comparator output is comparator out equals if in plus is greater than in minus, then the output is high. If in plus is less than in minus, then the output is going to be low. So the comparator, the two inputs, is usually we have one marked as the V reference. This is the value that we actually want to have the comparator compare against. And you have the voltage that the comparator is going to receive as an input. So anytime the comparator reaches the VREF threshold, the output will go high or low depending on the outcome. So for our comparator, our V reference, the voltage that we're going to compare against, we have set that to a DC voltage source of 2.5 volts. And our compare voltage, this is going to be our input. We have set it to a sine wave source. We have set that sine wave to be a DC offset of 2.5 with an amplitude of 2.5, which in LT Spice will give us a sine wave from 0 volts to 5 volts, and we will run it at 10 hertz. Now, since we're running it at 10 hertz, we will go ahead and set the simulation parameters. We will just have this thing run for 0.2 seconds. We just need 200 milliseconds. That should give us a couple signals so we can kind of see what is going on here. It'll just be a transient time run. So we're going to close that. So we will go ahead and run this. So here we can see we are looking at the comparator, our reference voltage, and our comparator out voltage. We'll go ahead and just make this a little bit bigger so we can see it. And when we're looking at this, we can see our reference voltage, 2.5 volts. We can see our sine wave going from 0 volts up to 5 volts. And we can see our comparator out because, remember the comparator out, anytime the in plus is greater than in minus, then we should see a high. Whenever in plus is less than in minus, we should see a low. Right now, our reference is set to the in minus pin, so this is a non-inverting comparator. And so every time the comparator voltage is greater than the VREF, we have a positive output, or we have our VCC rail. And anytime that the comparator voltage goes below our V reference, our comparator output goes to VSS. In this particular instance, our VSS is now set to ground. So you can see anytime that the comparator voltage is above the V reference, we hit VCC. And every time that the comparator voltage goes below VREF, our comparator out goes to ground. So now let us just see what happens when we turn this into an inverting comparator. To make it an inverting comparator, we just have to take the V reference and put it on the in plus pin, and now our comparator voltage is going on to the inverting input of the op amp. So now what will happen is we will have an inverted output. So anytime that the V reference is greater than V ref, we should see a low or ground, the VSS voltage. And anytime that the V reference, the V comparator, the comparator voltage is below the reference point, we should see an output of VCC on the output of the comparator. So let's go ahead and run that. So here you can see exactly what we thought would happen. The only thing that changed is our output signal became inverted. So now every time the comparator voltage is above V reference, we have an output low, and every time that the comparator voltage is below our reference voltage, we have an output of a high. So this is the inverting comparator arrangement. In both of these arrangements, in the inverting and the non-inverting comparator assortment though, you can see that we still are bound by the basic rule that whatever the comparator out, whenever n plus is greater than n minus, we have a high. Whenever n plus is less than n minus, we have a low. So this is true under all circumstances. The need for an inverting or a non-inverting comparator depends on what you want the output signal to be based on reference and based on your voltage that is going into the comparator that you're trying to compare. So with the comparator, the one thing you have to look out for is this reference point right here. If we have noise on the line, our V reference is usually pretty solid. Sometimes it's a little, depending on the reference voltage that we're using, it could not be as solid as this. It may in itself have some noise on it. There may be a voltage ripple of maybe, let's say 1 millivolt, right? 2 millivolts, 5 millivolts, depending on your voltage reference source. In addition to that, depending on what your comparator voltage is, you may not see a clean sine wave like this. Your signal may not be precise. And so what happens is, what could happen at this point is you could have some oscillation at the crossover point. So you think that you're only crossing one time, but if the comparator voltage and the reference voltage are noisy, going up and down, you're getting a slight differential right here, you could end up with a couple false triggers. And instead of having a nice, clean on-off signal coming out of the comparator, you could end up with a series of square waves coming up and down at a high frequency pulse. So in order to combat what could end up being a couple false triggers due to some oscillation on the line at the crossover point, there is something called hysteresis. So we can program in some hysteresis using two resistors. We have an input resistor and a feedback resistor. Now you may look at this and you may think, oh, that looks like an inverting amplifier, not a comparator with hysteresis. But one of the differences between an inverting amplifier and the comparator with hysteresis is a non-inverting amplifier. The input resistor and feedback resistor are joined at the inverting input of the op amp, the N minus. But for the comparator with hysteresis, you can see our input resistor and feedback resistor are connected to the non-inverting input of the op amp, the N plus pin. So that's how you can tell the difference between a comparator with hysteresis and an inverting amplifier, even though they look similar with the input resistor and the feedback resistor. So how do we calculate the hysteresis? The overall hysteresis, the total hysteresis around the reference point, will be equal to your Vs times your feedback resistor divided by your feedback resistor plus your input resistance. Now that is going to be your total hysteresis between your upper trip point and your lower trip point. And then in order to calculate your upper trip point and your lower trip point, these are the two formulas that you can use. So the upper trip point is your feedback resistor times your reference voltage plus your input resistance times your VCC, all over your input resistance plus your feedback resistance. And the lower trip point is the same formula, except instead of using VCC, you're using the VSS. And so in our system, the VCC is going to be our 5 volts and the VSS is our ground. Now I have a spreadsheet. I use Google Drive a lot to just do these maths so I can do some quick checks to see what I can do to change things. So you can see here, I've got my voltage reference set to 2.5 volts. I have my VCC set to 5 volts. I've set my feedback resistor to 5, my input resistor to 1. So you can see my overall hysteresis is going to be 0.83 volts. And so my upper trip point is 2.92 volts and my lower trip point is going to be 2.08 volts. So let's go ahead and run this and we will see what it does. And the thing is we don't want to look at the old comp out one, so we'll delete that trace while it's running, and we'll go ahead and add our hysteresis comparator output. So now we'll go ahead and take a look at this, and we will see now before, when we were looking at the regular comparator, if you recall, as soon as, make this a little bigger, as soon as the comparator voltage dropped below the reference voltage, right, on the inverting one, and we're in the inverting situation because our V reference is on the in plus pin, and we're using the inverting input for our comparator voltage. So as soon as our V reference dropped below the reference voltage, our output was going up because it was inverting comparator, but now we do not go up until sometime after we pass that V reference point. So it doesn't trip immediately, but now it trips at this lower level. And remember our math, we calculated that out, and it said our lower trip point was going to be 2.08 volts. So when we look here, we put our little mouse on there, you can see that our Y value is 2.08 volts. So pretty accurate in the math aspect. And then the same thing, so we come down, and when we're coming back up, we do not trip immediately after crossing over that threshold, but instead we wait till the upper trip point up here, and you can see that that is about 2.9 volts. And so 2.92 was our calculated voltage. So now we can use this, and we can see what we can do about changing that trip point. So let's see what happens if I put a 10K resistor as my feedback. You can see that now our hysteresis gets a little tighter, right? Instead of having an 830 millivolt hysteresis swing, I've now got a 450 millivolt swing. And if I take that up even higher, you can see it's now it's only 24 millivolts swing, so 2.62 and 2.38. So let's go ahead and just put that in. We'll change out our feedback resistor for 20K. And I'm using parameters, so I can just come up here, change my RF to 20K. And then we run that again. And so remember, we had the upper trip point was about 2.62. So if we go over here, where's our upper trip point? About 2.62. And our lower trip point was 2.38. So you can see our lower trip point was 2.38. Again, the values are right down here that we're looking at. You can see 2.38. So when you're using this comparator, you want to kind of determine what is it that you want your upper trip point, your lower trip point, how much hysteresis do you want on your output, because you don't want to constantly be tripping on that crossover point. So you want to give yourself a little bit of hysteresis if you need it to overcome that. So now, just like with the other comparator without hysteresis, we were able to turn it into a non-inverting and an inverting comparator by just swapping these two. So right now, like we saw, this is an inverting comparator, meaning anytime that the voltage is above our reference, then we get a low on the output, and anytime our comparator voltage is below our reference point, we get an output of a high. But if we want it to work as a non-inverting comparator, same thing as with the normal comparator, we just put our reference on the inverting input, and we put our comparator voltage on the non-inverting input of the op amp. We don't have to change around the feedback resistors. The hysteresis still works as it is, except now, when we run it, we'll have a non-inverting comparator. So anytime that our voltage level is above our reference, we have an output of a high, and anytime our comparator voltage is below our reference, we have an output of a low. So you can see there, comparator voltage above reference, we got a high. Comparator voltage below the reference, we have a low. So that's the comparator op amp. I hope you enjoyed it. Please like, subscribe, comment down below, and I will see you next time.